So we will calculate the work done during an adiabatic process which happens quasi-statically. So you know that in adiabatic process the system is perfectly isolated from the surrounding so that no heat flow occurs between the system and the surrounding. And the thing to be taken care is that all the three thermodynamic variables, the pressure, volume and temperature, undergo change here. Okay. Now we can start with the expression for work done for any finite quasi-static process involving a changing volume given by W equal to minus integral from Vi to Vf P dV. This is the point where we start our derivations in all the four cases where you have to calculate the work done. Now, since we are considering a quasi-static process, at every stage of the process, the equation of state will be valid. Hence, I can use the equation of state for adiabatic process. For adiabatic process, the equation of state is PV raised to gamma. You know, it is written in three different forms. I am using one of the familiar forms, PV raised to gamma equal to a constant. So let's call that constant as some K. So let me say this is my second equation. Now I need to substitute for the P here. So let me rewrite equation number 2 in terms of the P. Therefore P is equal to, I can take V raised to gamma to the other side, so it will become K V raised to minus gamma. Say that this is equation number 3. So we consider the system to be going from an initial state Pi, Vi, Ti shown here in the graph on the right to a final state denoted by the macro state Pf, Vf, Tf. So two graphs are shown here, one corresponding to an expansion and the other corresponding to a compression. So you can see the only difference here is the initial states are denoted separately, and also the arrow on the process graph has been reversed. So any one of these graphs can be used. So I will substitute now in equation number 1. Therefore equation number 1 becomes, let's see what is equation number 1 turning out to be. Equation number 1 becomes W equals work during adiabatic process equals minus integral. So I can substitute, so of course the limits are from Vi to Vf. I can substitute for P as K V raised to minus gamma dV. K V raised to minus gamma dV. So you know the advantage of this substitution. We could get rid of the P term because we are doing the integration with respect to volume. So every other quantities other than volume can be made as constant by this particular step. Now I can continue with the process of integration, you know. Okay, so if you want you can just take K outside, but I'm keeping it as such for some reason which will be evident now. So it is equal to K times, so it is one of the simple integrals, x raised to n dx. So it will be x raised to n plus 1 by n plus 1. So what will be the thing? It will be K into V raised to minus gamma, right? Minus gamma plus 1 by gamma minus gamma plus 1 minus gamma plus 1. So that is the integration. So where I have used the common integral x raised to n dx. So I have to retain the limits Vi to Vf, Vi to Vf. So let me make the substitution. I am taking this there was a negative sign here, there was a negative sign here. So when I take the negative sign, when I consider the negative sign, it becomes equal to 1 divided by, I am rewriting this one as 1 divided by, using this negative sign I can reverse the sign of the denominator here. It will be equal to gamma minus 1 1 by gamma minus 1. Let me use a square bracket. So what left out is k v raised to minus gamma, right? There is minus gamma plus 1. So let me do one thing. I am separating that thing as k v raised to minus gamma times v. Nothing wrong in it, So it is nothing but v raised to minus gamma plus, it is v raised to minus gamma into v. I'm separating out x raised to a into x raised to b equal to x raised to a plus b. I'm using that idea. So once again, it is from Vi to Vf itself, Vi to Vf itself. Now what is the advantage of making this modification? You will see that I'm getting k into v raised to minus gamma. So is it not of equation number 3 form? Yes. So if I substitute the upper and lower limits, what I'll be getting, it's further equal to 1 divided by gamma minus 1 times, let me open the bracket, I'm substituting for the limits. So k Vf, upper limit is Vf raised to minus gamma times Vf minus upper limit value minus lower limit value. So what do you think? K Vi raised to gamma times Vi. So that gives you the integral. Now this kv is equal to p. So kv raised to minus gamma equal to p as per equation number 3. So what about the first term here? That will be pf. And what about the second term over here? That will be pi. So I can write this is equal to, that is equal to 1 by gamma minus 1 times pf along with that Vf is there. What is remaining? Minus pi Vi. Pf minus pi Vi. Okay. Now I can once again modify this one, because it's of the form PV and we are dealing with an ideal gas system. For an ideal gas system, PV equal to nRT. PV equal to nRT. So I am writing here PV should be equal to nRT. And as we have seen earlier, during adiabatic process, along with change in pressure and volume, there will be a corresponding change in the temperature also. So corresponding to Pi Vi, the temperature is Ti, as can be seen from the graph initial point here. And corresponding to Pf Vf, the temperature is Tf. So I can write Pv, I am rewriting this one as 1 by gamma minus 1 by gamma minus 1 times Pf Vf, I can write as Nr, Pv equal to nRT. So Pf Vf should be equal to Nr times Tf minus Pi Vi should be equal to Nr Ti. I'm just substituting Pv equal to nRT. So you could have avoided one of the steps here, but I'm just carrying it forward. So this Nr is constant over here. So I can take Nr outside. So it will be equal to Nr divided by gamma minus 1 times Tf minus Ti. Tf minus Ti. Nr divided by gamma minus 1 times Tf minus Ti. And this one can be, this is a very prompt equation. So this is the work done for adiabatic case. Equation number 4. Hope the derivation is okay with you. So you can see, you can write this equation in several other forms. You can change the denominator as 1 minus gamma, so there will be a negative sign. So the numerator, the Ti Tf sign also will be getting reversed. It will become Ti minus Tf. So better I suggest let us follow this form of the equation. That will be an equation without a negative sign in the beginning, and moreover gamma is usually greater than 1. So since gamma greater than 1, when you do the numericals, automatically you will be getting this first set of quantities as a positive number. Then depending on whether it is a compression or it is an expansion, you will be either getting a negative sign for the quantity in the bracket or a positive sign, which will render the work done as either positive or negative. Now let us check the sign conventions also. So by sign conventions, during compression, case 1, so let's say case 1, so during, let's take compression, so let's take what is happening during compression. Let's check our sign convention. We have seen that W is compression means work is done on the system, so work done is taken to be positive. So W is positive. So when do you get W positive? Nr by gamma minus 1 is already positive, because gamma is greater than for gases. So whether W will be positive or negative will depend upon the quantity in the bracket. So what is the meaning? That is Tf minus Ti is positive, greater than 0, right? And what is the natural conclusion? It means that Tf greater than Ti. Final temperature is greater than the initial temperature. And I think this is the same idea that we have discussed conceptually also. During adiabatic compression, the internal energy of the system increases, and you can see that as a result the temperature of the system also will be increasing. So heating occurs. You can see that the temperature increases or temperature increases. That is the normal conclusion. And you can consider the reverse of the case as case 2 during expansion. So automatically you will get the reverse of the thing. W is negative, that is our convention. Hence Tf minus Ti must be, as per equation number 4, that must be less than 0, and it denotes that Tf is less than Ti, and it denotes that an adiabatic expansion result in cooling or temperature will be getting reduced. So this is the discussion of the work done during a quasi-static adiabatic process on a simple system like ideal gas. Now let me add one more thing here. Hope you remember I told you work done in thermodynamics is in general a path dependent function, or it is taken as an inexact differential. But during the definition of the first law of thermodynamics to begin with, we have taken that adiabatic work has got certain role. So let us revisit our equation for first law of thermodynamics, which was given as du equal to, let me use maybe a different color to avoid. Yes, so let me use du equal to, this one was our first law of thermodynamics, du equal to d bar q plus d bar w. Okay, now we have seen for an adiabatic process, d bar q is equal to 0 because no heat enters or leaves the system. So what will be du equal to? Du will become entirely equal to d bar w, and this work is what is known as adiabatic work. Now on the left side you see du. What is du? It is u final minus u initial. Now just have a look at this equation. What does it mean? On left side you have got u final minus u initial, that is a change in the internal energy, and the internal energy is a state function. And on the right side you have got adiabatic work. So the equation tells you that the adiabatic work can be found out just from the final value of a state function minus the initial value of a state function. So you can see that as per the equation, the adiabatic work depends only on the initial and final states of the system. It does not depend upon the intermediate states through which the system passes through. And this is exactly in contradiction or difference with what we have stated earlier, that work in thermodynamics is path dependent. So remember, this is an exception. This is an exception. Okay, in general, work in thermodynamics is path dependent except adiabatic work. Adiabatic work is path independent. Adiabatic work is path independent. So you can even write the first law of thermodynamics this way: u of minus ui is equal to w adiabatic. That also you can write if you are considering a finite process. So just remember that fact also. We conclude this session here. Thank you.